Modern open web data collection relies on environments that are highly unstable. Target websites are structurally heterogeneous, where DOM layouts and selectors constantly flicker and shift. The industry's current solution is to deploy autonomous React agents, relying on them to write and execute scraper code in real time as they navigate these pages. But direct LLM code generation fails under live conditions. The models consistently produce dependency errors, output schema mismatches, and latch onto broken DOM selectors. Executable scripts require absolute structural rigidity to function. Language model reasoning introduces stochastic inconsistency by design. From an engineering standpoint, the two are structurally incompatible. Combining a brittle web architecture with a hallucination-prone agent guarantees a fragile, unscalable pipeline. To fix this, system architects must stop asking LLMs to execute code during runtime. The alternative is shifting the language model's output entirely to an isolated pre-execution configuration stage. Instead of generating free-form Python or Selenium scripts, this pre-execution configuration must be strictly typed JSON. This restriction shifts the language model's role from a live, active operator to an upfront architect. This architecture converts stochastic reasoning into a set of fixed, auditable instructions suitable for enterprise pipelines. This decoupling relies on a strict, multi-stage framework, beginning with the requirement understanding agent. Its sole job is to ingest a messy, natural language request and immediately probe the target web source to extract context. The agent takes that contextual data and forces all incoming requests into a rigid taxonomy. There are exactly 6 acceptable categories: search, list, detail, API, interactive, and file. Every type operates within explicit functional boundaries. A list collector is strictly prohibited from executing deep content extraction, restricting it entirely to traversing paginated list pages. These boundaries prevent the agent from attempting sprawling, multi-step tasks that it cannot reliably finish on its own. The proactive probing provides structured priors, like accurate page titles and column layouts, ensuring the agent doesn't misclassify the request based on vague instructions. By constraining the initial input into this rigid taxonomy, the system prevents the generation of any configuration that lacks a mathematically clear execution pattern. Once the requirement is typed, it passes to the collector instantiation agent. This agent operates under a hard operational constraint. It is completely banned from writing executable code logic. Instead, it relies on template slot filling. The model is only permitted to drop specific variables, like target URLs and DOM selectors, into predefined JSON schema slots. The templates surrounding these slots hardcode all necessary error handling, pre-built utility functions, and persistence logic. Replacing unconstrained generation with typed slot filling eliminates syntax errors and API mismatches before execution even begins. The instantiated JSON configuration then moves into the execution phase. It is deployed to an Apache Airflow Directed Acyclic Graph, or DAG, which acts as the static, deterministic execution engine. A generic collector operator reads the JSON configuration interpretively to perform the extraction. Because the language model is entirely removed from the execution environment, the runtime behavior becomes 100% predictable. Standard runtime LLM baselines consume between 3,400 and 4,200 tokens every time they attempt a collection task. This constrained framework consumes exactly 0 tokens during the execution stage. This 0-token execution dramatically lowers the average wall clock time, cutting runtime to roughly 5 seconds compared to the 15 to 20 seconds standard for React models. The initial compute cost of generating the configuration is amortized over thousands of future scheduled runs. Intelligence should be a one-time architectural cost, not a recurring execution tax. If the instantiation agent generates an incorrect JSON configuration, the static pipeline will break. The framework relies on a quality check module that evaluates validation runs using deterministic rules, entirely bypassing subjective LLM judgment. It scores the data across 5 precise dimensions: structure, content, relevance, attachment, and execution. If a configuration fails this assessment, the resulting quality report immediately triggers the feedback correction module. This module uses a routing logic known as Algorithm 1, which relies heavily on a failure blacklist. Failed DOM selectors Broken field paths and invalid hypotheses are logged directly onto this blacklist. The language model is forced to regenerate the configuration under these new negative constraints, pruning away dead ends. Standard self-reflection models routinely fail to identify errors in their own code. This workflow isolates the error via external rule evaluation before the LLM even sees it. Designing an external evaluator makes failure an auditable, traceable signal rather than a silent system collapse. Controlled feedback experiments on a 138-task dataset prove the efficacy of this constraint loop. Without a feedback loop, the initial pass rate for defective configurations sits at 0.007. Once rule-based correction is applied, it hits the absolute ceiling at 1.0, requiring an average of only 2 rounds to generate a flawless configuration. The pass rate reaches these levels without requiring changes or upgrades to the underlying foundation model. Achieving perfect reliability doesn't require a smarter foundation model, it requires a stricter algorithmic boundary. It is true that runtime LLM baselines score slightly higher on purely one-shot, first-try extraction quality. Sacrificing a minor amount of one-shot quality is a necessary engineering trade-off for scalability. You can choose high initial quality paired with massive token drain, or moderate one-shot quality paired with high reliability and zero runtime cost. Enterprise schedules running thousands of daily web queries demand deterministic consistency, not one-off brilliance. Removing language models from the execution path creates a reusable, highly stable data collection engine. By prioritizing auditable constraints over unconstrained reasoning, the framework ensures that controlled, explicit failure is a more stable engineering choice than uncontrolled, silent success.